Hello student, welcome back. In this video class, we will discuss about thermodynamic properties of ideal solution. This unit, you will get the question like this. Derive an expression for Gibbs free energy of mixing. As we know that Gibbs free energy is denoted by delta G. It is a change in Gibbs free energy. So for an ideal solution, in this solution you have to derive enthalpy of mixing equal to 0, enthalpy volume change equal to 0, enthalpy change equal to 0, and entropy change equal to 0. So this is one of the very important topic in the solution, ideal solution, thermodynamic properties of ideal solution. So suppose you have a container A and B. When A and B, let's say N1 moles in A and N2 moles in B, and that give a binary mixture. When binary mixture is formed by component A and B solvent. So suppose a solution, this is a solution. Suppose a solution is formed by mixing Na, that is in Na moles of a liquid, that means the solvent number A in this, and Nb moles of a liquid in B. So the Gibbs free energy is change in Gibbs free energy here, delta G equal to G solution. That means Gibbs free energy changes, the change in free energy is equal to the Gibbs energy of the solution minus the pure solvent, Gibbs energy of pure solvent, that is Ga or Gp. This is a solution and this is a pure. So per moles in this, if you have a per moles of solution, if you have a per moles, in per moles you have, suppose Ga is a Gibbs free energy of A component, A in solution, and Gp is a Gibbs free energy of B in solution, and Ga bar equal to Gibbs free energy of A if the solution is pure, or G bar B equal to change in free energy of B if pure. So if we consider these parameters for per moles of the solutions, you get this G solution equal to Gibbs free energy solution equal to N moles in Gibbs energy of solution A plus NB Gibbs free energy B. Let us consider equation number 1, or this as this. So for A, since you are considering the components of two component mixtures, for if the solution is Gibbs free energy is pure, for pure component, if you have a pure component, Na and Ga bar plus NP Gp bar you will get. So this entropy of mixing, Gibbs free energy of mixing equal to, since you know that the Gibbs free energy has a Na G Gibbs free energy of solution minus pure, right? So this you will get Na Ga plus NP Gp you will get minus what is that for pure Na Ga bar plus NP Gp bar you will get. So take in the command. If you take Na as command, you will get Ga minus Ga bar you will get, take in the command, plus NP you will get, and Gp minus Gp bar you will get. So we are rearranging this equation only. So considering all these things, you will get Na Ga minus Ga bar plus NP Gp minus Gp bar. Okay, so but since you know that you have since in the solution, in these solutions A and P, N A moles and P moles, right? So there is a change in the chemical potential. So for chemical potential change, you know that Ga equal to G bar plus RT ln x or you can have A ln A. This is A and this is A. So this A is nothing but it is the activities in the solutions. So this is a Gibbs free energy change. So by this Ga value we will be using this. So for Gibbs free energy in this component A is this much. So let us say you have a Ga, you get bar is equal to Ga bar. This Ga is nothing but it is a Gibbs free energy change in the solution to component A, and G bar is the Gibbs free energy change in the pure solution A, that they are equal. So Ga minus equal to Ga bar equal to RT ln activities A component you will get, where A is the activities. So for enthalpy of mixing, this delta G of mixing you will get Na RT ln A for component A plus NP number of moles in P and RT ln AP for component P you will get. But for ideal solution, this A component activities A is equal to mole fraction, right? So this delta G of mixing become Na RT ln XA, or this delta G of mixing is become summation Ni RT ln Xi you will get. So for per moles of Gibbs free energies, for per moles, this is in mixing, for per moles this Gibbs energy delta G of mixing divided by moles of component A into moles of component P you will get. So this equation, if we rearrange in summation Ni RT, since this delta G is this one, we will use RT ln Xi divided by Na, this one, plus NP you will get. So I'm writing here, you will get this delta G of mixing per moles equal to XA RT ln XA plus XP RT ln X in component P. That is, therefore, delta G of mixing of per mole equal to what you will get, summation N Ni RT ln Xi. So this is for the entropy of mixing solution. This Xi is nothing but it is a mole fraction. This is a mole fraction in the solution, and it is always less than, unity. Thus delta G of mixing become negative, or delta G is always negative quantity. So this is the entropy of mixing of equation you will get. But the question asks about, you have to show a volume of mixing is equal to 0, enthalpy is equal to 0, and entropy is equal to 0. So one thing you have to keep in mind is, when the solution is mixing, binary solution is formed, the chemical potentials and keeps the equilibrium is maintained, and keeps free energy and chemical potential is RT ln XA. All these are changes, but here the volume becomes 0, and enthalpy also 0, and the destruction of molecules, the randomness of molecules, that is entropy, also 0. So you have to show these three in a detailed manner. So suppose you have a volume change of mixing in this solution. Volume change of mixing, since you know that for thermodynamic quantity of Gibbs free energy change of mixing equal to change in pressure equal to 0. But here we have proved that Gibbs free energy of mixing equal to Na moles of RT ln XA plus in N molecules in PT RT ln XP. This is the equation that from the component of these two. But here, since change in Gibbs free energy change in temperature, pressure equal to 0, equal to entropies. This is from thermodynamic quantity. From thermodynamic quantity, you get that change in Gibbs free energy due to temperature is equal to 0. Small change in Gibbs free energy to that of temperature at constant pressure equal to entropy of change in entropies, and change in volume is change in delta G by delta pressure at constant temperature equal to change in volume. This you have derived in the chemical potentials. So by knowing these things, since this change in Gibbs free energy of mixing we are calculating, so at change with pressure, whereas at the constant temperature is maintained, so this enthalpy of mixing volume in the component these solutions, it becomes 0, because when the temperature is constant, the volume also become constant. So this volume of mixing equal to 0 you will get. Yes, change in enthalpy, a change in volume of mixing equal to 0. In any given solution, when the temperature is 0, the in any given solution when the temperature is 0, the volume become 0. So this is the one type of solution. Volume change in mixing is always 0. And another changes is change in enthalpy of mixing. Enthalpy of mixing, that is a enthalpy change of mixing. Let's say this is enthalpy change of mixing. So since you know that delta G of mixing divided by T equal to, in component A, N A R T L N X A plus N P R T L N X P, it is divided by T. We are taking the common temperature T. So this equation become, let's say this is equation number 1. So this delta G of mixing, let's say, is divided by T equal to, this T and T will cancel, and the remaining you will get Na R Ln Xa in component A and Np R Ln Xp in component B you will get. So by this solution you get that the change in the whole square change in Gibbs free energy of mixing by T is overall change in temperature at constant pressure is equal to 0, because all this quantity becomes 0. Thus the small change in Gibbs free energy of mixing divided by change in temperature at constant pressure equal to minus delta enthalpy mixing by T2. Continuation only, this one. Thus, therefore, this minus enthalpy of mixing by T2 become 0. That is, therefore, enthalpy of mixing equal to 0. So this is how the enthalpy of mixing in the binary solution become 0. But when the molecules of suppose you are considering the same component only A, P, when the solutions of binary solution is formed, the molecules of the solid A and B become destroyed. So the randomness of the molecules also changes. It also disturbs. So this tree is entropy change of mixing. Entropy change of mixing for an ideal solutions. Since you know that the Gibbs free energy delta G is equal to change in enthalpy minus temperature change in. This is the equation that Gibbs free energy, Gibbs-Hellman equation. From the Gibbs-Hellman equation you get this, right? So this, but change in Gibbs free energy of mixing equal to this enthalpy of change in enthalpy also become enthalpy of mixing and minus T delta entropy of mixing, Gibbs free energy, enthalpy and entropies. But since you know that this enthalpy in the enthalpy is 0, So this Gibbs energy of mixing equal to, this will become 0 minus T delta S mixing you will get. So this, by rearranging this equation, entropy of mixing minus, if you come this side it will become minus delta G mixing minus what is remaining, it will go downside T. But since you know that this Gibbs free energy of mixing equal to Na component RT ln XA plus NP RT ln XP, right? For this Gibbs free energy, therefore this divided by T you will keep. This entropy is S, it is denoted by S. So entropy of mixing, why it is mixing? Because we are studying the thermodynamic binary solution. So delta X mixing equal to minus Na, here we have a minus sign is here, right? So this minus Na R ln XA minus NP R ln XP you will get. So these solutions, delta X of mixing equal to minus summation Ni R ln Xi you will get by this I. This delta X S of mixing equal to, since we are for the per mole of the solutions, if we consider as single moles, this whole of the solution become summation I Xi, that is a mole fraction case constant in the solution, logarithm of Xi. So when these all are constant, you will get in the solution you will get delta X of mixing equal to plus enthalpy of mixing. So this is the solution of yes. So this entropy of mixing of solution is not equal to 0, but it is positive. It's positive. So these are the three types of thermodynamic quantitative changes in the ideal solutions. If you have any problems, you can ask. We'll discuss in the next class. Thank you for watching the video.